Good evening. My name is Antonio Rago and I'm a theoretical physicist, and I'm here tonight to tell all of you how successful physicists are in describing everything, ranging from the size of elementary particle up to the size of the entire universe. Or maybe I'm going to tell you what we just don't understand. Okay, let's start. Tonight I'm going to tell you about just two of the most beautiful theories physicists have created. The left one is the standard model. It describes the interaction of every single elementary particle and their interactions. Is it electromagnetics, like electricity, or the light that comes from the sun? Weak, the force responsible for radioactive decay, or force that is strong, the force that keeps together nuclear matter. Or, in the other case, I will tell you about the masterpiece of Albert Einstein, general relativity, the theory that tells how energy and matter act on space and time, bending them to give rise to gravity. These two are two terrible predictive theories. They are capable of making prediction out of measurement as precise as 10 million of millions in precision. Imagine you make a measurement and then you can predict this measurement for 13 digits of precision. It's impressive. Yet I'm a physicist, and as such, and as my community does, we go around to look for pitfalls in our theories. So we build experiments. And in order to study the first of these theories, we built the LHC. It is the most gigantic experiment ever built on Earth. It's a ring, just a ring, 27 kilometers diameter, buried 100 meters under the ground. LHC is in Geneva. And what it does, it just accelerates a bunch of protons up to a speed that is 99,9999991% the speed of light. And it makes it collide against another bunch of protons that is rotating in the opposite direction. More or less like this. And we just look for the outcome of this collision. You may think of this as taking two cars and smashing them together, and then going around and looking for the outcome. Oh, this is a wheel. Okay, works more or less like that. It doesn't work too well. There is something strange of particle physics. We know very well that when you collide two particles, it may happen that you end up with a third particle that is actually heavier than the two original particles. And no one here hopes that you take two Vauxhall cars, you smash them together, and you get a Ferrari. Okay, it works like that for particle physics. So we switch on the LHC, and we start one out of the other to find all known particles, up to the last one. And the entire physics community is super excited. Yeah. Every time we find a particle, we are super excited. No, wait. This one is special. It is the Higgs Boson. You may have heard of it as when it was discovered in 2012, it had a great, huge, really, media coverage. The special property of the Higgs is that it emits a field. What's a field? We all have an experience of a field. Whenever you take a magnet and a piece of metal, you will feel that the magnet and the piece of metal are attracting each other. This is the result of the magnetic field. Well, the Higgs field is something similar, with a major difference is that the Higgs field percolates the entire universe. And this is just by means of the interaction with the Higgs field that every single elementary particle gets mass. Hard to imagine. No, wait, it's easy. Think of the Higgs field as a gigantic pond of treacle. The more you interact with the treacle, the heavier you are. The less you interact with the treacle, the lighter you are. So you may understand that as this Higgs field is at the basis of the mass of the entire set of elementary particles, we really needed it. It's the cornerstone of our building the Standard Model. It was predicted, and we needed it to build the Standard Model. So, in the end, when we found it, we were very excited. But as soon as we found it, in our mathematical understanding, we already knew that there was something wrong. Indeed, the Higgs field, in our opinion, is either on or off. And when I mean off, I mean zero, nothing, null, nowhere. And when I mean on, it's terribly on. And instead, we measured it. And what we discovered is that the Higgs field is neither on nor off. It's actually, you know, this switch that cannot switch off properly. It's a bit broken switch. And to be honest with you, this is our luck. Since should the Higgs field ever had a value that is in any way different from its actual value, all the known matter would collapse in point-like objects. Not too bad for someone who started saying we do understand everything. Okay, maybe I should have been more humble and say, we are very good in particle physics, but we don't know where the mass comes from and the energy of the particle and their origin. Wait, that's just the first of the open question of tonight. Maybe it's going to get worse. I spoke about two theories. And the second theory is the theory of relativity, of Albert Einstein. And when I speak about relativity, I think about gravity, so interaction of planets, stars, galaxies, clusters. And what do you do as an experiment is just you take a picture of the sky in all the possible different electromagnetic ranges, but it's just a picture of the sky. This is, for example, the Gaia telescope. And what we do is we just take this picture and we classify our findings. This is a galaxy, this is a star. And you may end up finding something like this. Beautiful, isn't it? It's a rotating galaxy. It's an object that contains something between 1 million and 1 billion of stars. And at this scale, you cannot distinguish what the solar system is. And what is interesting of this object is that it rotates around its axis. And out of everyday experience, we would expect that as the vast majority of mass is in the middle, the speed of rotation of the middle should be higher than the speed of rotation of the objects that are farther out. Let me give you, as usual, an example. Think of a cappuccino, okay? You look at the foam, and you start to stir it with your teaspoon. The foam in the middle will spin faster than the foam closer to the border, okay? It has to work like that, more or less. So we went there and we measured it. And what we found was a surprise. Yeah. What we found was that the speed of rotation of that galaxy is practically constant. It's the same in the middle and out. No, wait, this is wrong. We can't understand it. I mean, it's so wrong that we have to imagine that there is something hidden in that picture that I'm not seeing. There must be something else in this picture. But I can't see it, so I call it dark. Wait, whenever a physicist tells you dark, it mostly means we don't understand it, okay? So dark, no, we don't understand it. Good. Anyway, let's assume that there is something dark, and it's interacting gravitationally. So let's call it dark matter. And let's count how much dark matter do I need in order for the galaxy to spin, to rotate properly. Okay, very good. I can do the calculation and scale it up to the size of the entire universe. And what I discover is that, oh my God, bright matter, the matter that we know, that I have described so far with my beautiful theories, is just 15% of the balance of mass of the entire universe. I need, just to explain the rotating structure, an 85% of dark matter. Not too bad. We do understand everything. Wait, this is just the second open question. I said the 3 open question. Oh. Okay, a third point that I want to tell you about is that what we believe, and what we have actually measured very precisely, is that our universe is expanding. If I measure, and if I look at every other point and object that is around me, I will see it
going away. How do I understand that? Well, in our opinion, what it happened is that more or less 14 billions of years ago, everything, all the structure, was collapsed in a single point in space and time. And then a fluctuation, an explosion, gave rise to all the known structure. Starting from a small blob of a very energetic, hot and dense plasma that then eventually flew out of the explosion. Very good. It makes sense, out of an explosion, you are sitting on a piece of debris, call it Earth, and you're looking around you and everything is going away. Fine, it works, good. Wait. What I would expect, should that be the case, is that all these bits and pieces are interacting only gravitationally. Good. But I would also expect that the relative speed with respect to every other object I see around should decrease. Let me give you an example. Consider for a moment a stone, a pebble from the beach. The Earth and the stone interact, okay? They attract each other gravitationally. And let's imagine an explosion. Myself taking the stone and throwing it in the air, okay? What will happen is, as soon as the stone leaves my hand, the speed of the stone with respect to the Earth will decrease. Will get slower and slower, and eventually will stop and fall to the ground. But this is only due to the fact that I'm not strong enough to throw the stone out of the influence of the gravitational field of the Earth. Should have been strong enough, the stone could leave the Earth. But yet, I would expect that the relative speed of the stone with the Earth should decrease with time. Okay, this is our expectation, and then we can go and measure it. And we can measure the speed of the expansion of the universe 1 billion of years ago, and the speed of the expansion of the universe today. And what we discover is that the speed of the expansion of the universe 1 billion of years ago was smaller than today. Wait, smaller. The universe is accelerating. No, cannot be. What's going on? I mean, in order for something to be accelerating, it needs an engine, a propeller, something that pulls out you from the interaction with the other bodies. No, it can be. I don't understand it. Okay, I call it dark and that's it. But is fueling this explosion, so I call it dark energy. Very good. Terrible. So I can go back to the drawing board, I'm a physicist, and I can evaluate how much dark energy do I need in such a way that the universe could expand at the rate at which it's expanding. And then I need to compare it with something. And thanks again to Albert Einstein, using the famous relation E equal mc squared, I can compare energy with mass. So let me compare energy with, let's say, the mass of the universe. Something comparable, okay? And what I discover is that in the balance of mass and energy of the entire universe, what we know nowadays is the bright matter, just 5%. The dark matter, the object that I need for the universe to rotate properly, is 27%. And what I need to let the universe accelerate properly, dark energy, is 68%. Now, my talk ends here, as I clearly don't have any answer for these three open questions. The origin of mass for the particles, the nature of dark matter, and a possible explanation for dark energy. There are candidates, theory candidates, that could explain the origin of the mass. There are possible matter candidates for the dark matter. And there are possible explanations for the structure of dark energy. But these are just theories that need to be validated. And maybe that's the reason why it's great to be a physicist today. Thank you very much.